All right, good afternoon. So the idea behind cofitting is basically to represent a given set of data in a polynomial. For example, or say we have some data xi, yi, where I goes from 0 to whatever it gets to n. And then we are told to fit this set of data in the curve. Our curve could be a polynomial of degree 1, so a naught plus a1x, could be degree 2, a2x squared, and so on, and so on. For the sake of this course, we'll be stopping at a polynomial of degree 2. So required to fit set of data for a polynomial of degree 1 and degree 2. All right. Now there are different methods of which we can do this. The first one is the least square approximation method. The least square approximation method. Okay. So since our given data here are discrete, we'll be looking at discrete least square approximation. That is, we are saying, okay, let's start with a polynomial of degree 1. So say our y is required to be a naught plus a1x. So we want to get the values or the value of a naught and a1 that will minimize or that will fit this data in this polynomial. Okay, so the first thing we do is we get a particular residue. Our residue, the residue s is given as s equal to summation I from 1 to n yi minus yi to power 2, where yi is equal to a naught plus a1 xi. So it means that we'll be having our s to be equal to summation I from 1 to n yi minus a naught minus a1 xi to power 2. Now for we to get the values of a naught, a1, we must minimize our residue. We must find that thing that minimizes our residue, that is at minimum residue from our calculus. At minimum residue, we know that our the s, the ai should be zero. So I want to go and differentiate our s with respect to a naught and a1 to get our what minimizes residue. So since we already said our s is equal to summation I from 1 to n yi minus a naught minus a1 xi to power 2, then our ds, the ai, or our ds, the a naught should be minus 2 summation I from 1 to n. We want to differentiate our a naught. Don't forget our 2 is coming down. Differentiating a naught here, we get minus 1. That's why you have y minus a naught minus a1 xi. Remember, it is taking, say you have y to be equal to f of x to power 2. You say your y prime should be equal to 2 f prime of x times f of x. So that's what we've done here. We have taken this 2 down, differentiate this whole function here, we get minus 1, then write this same thing back. So we have this. So if that is clear, remember we said we want to find that thing that minimizes the residue. So our ds, the a naught equal to 0 would imply that minus 2 summation I from 1 to n y minus a naught minus a1 xi should be equal to 0, which also implies that summation I from 1 to n y minus a naught minus a1 xi should be 0. We are removing 2. We are saying divide both sides by minus 2 so that the one goes away. Of course, you know that summation a plus b is equal to summation a plus summation b. So this equation here can become summation I from 1 to n y. Sorry, we have omitted something. It is supposed to be yi. So let me bring out this I. It's supposed to be summation yi minus summation I from 1 to n a naught minus summation I from 1 to n a1 xi, which is equal to 0. Don't forget the goal is to get a naught and a1. So from here I can see that we know that whenever we have summation 1 from I goes from 1 to n, is the same thing as n. So basically summation of a constant a from 1 to n should be equal to na. So it means that here we can say that our summation a naught I go from 1 to n should be na naught. It should be na naught. So if that is clear, we can have this line from here to give us summation I from 1 to n yi minus na naught minus summation I from 1 to n aixi equal to 0. In fact, we can say this is the same thing as summation I from 1 to n yi minus na naught minus ai summation I from 1 to n xi, which is 0. Now, why are we not saying that our summation yi should be nyi? The reason is quite clear, or it is very basic, because our y values are not constant. They are not constant to be determined. A naught is what we want to get, and a1, not x and y. Our x and y values are given. Remember, we said that we are taking our points to be from xi, yi. So we know a particular x naught, y naught. We know x1, y1. Do we get? So these values here are not exactly the same. So what we'll be having, so it will mean that our summation yi, it means y naught plus y1 plus y2 and so on. They are different values. Our summation a naught is the same thing as a naught plus a naught n times the same value repeating itself n times. But here they are of different values. That is why we are not saying that it should be nyi at this point here. So from here you want to get a naught, so it means that this line here can then become a naught equal to summation I from 1 to n yi, this one staying, minus a1 summation I from 1 to n xi over n over n over n. This would be our a naught. But then remember, we don't know what a1 is. So this would be wrong for us to say that this is our a naught. So we have to go and get a1 also so that we can put a1 inside this place. Let me term this equation 1. Remember, everything we've done so far is from the s, the a naught. We still have to take care of the s, the a1. So let's see. What will make the s, the a1? What will make it 0? So it will imply that we'll be having our derivative to be, again, minus 2 summation I from 1 to n. Differentiating x, differentiation of this here to a1 means I'll be having minus xi. Right? So here I should be having minus xi, then times y1 or yi minus a naught minus a1 xi, and then it should be 0. It should be 0. Don't forget our xi is is a variable. We can see it is a variable. So our minus you can go away. We have this to imply that summation I from 1 to n xi into yi minus a naught minus a1 xi, and it should be 0. It should be 0. Of course, we can expand all of this so that we have summation xi, yi, and so on. Okay, so it implies that we should have So it implies that this line should give us summation I from 1 to n xi yi minus summation I from 1 to n xi a naught minus summation I from 1 to n a1 xi square, everything equals to 0. Don't forget the goal is to get a naught and a1 in this place. So again, we can have our summation I from 1 to n xi yi staying, because our I is the counter, so they can't come out of the summation. Here our a naught can go away, so we have this to be minus a naught summation I from 1 to n xi. This one is the same thing, minus a1 summation I from 1 to n xi square, everything is equal to 0. Now we already know that we already know what a naught is in terms of a1. So why don't we bring this guy inside this place, so that we can remove our a naught, so that we can get what a1 should be. Okay, so let's do that. But our a naught is equal to summation I from 1 to n yi minus a1 summation I from 1 to n xi over n. So this line here becomes summation I from 1 to n xi yi minus so a naught is going away, I have this to be summation I from 1 to n yi, all right, minus a1 summation I from 1 to n xi over n minus a1 summation I from 1 to n xi square, everything is equal to 0. Everything is equal to 0. Everything is equal to 0. Oh, sorry. There should be another summation I from 1 to n xia. Don't forget, this is a naught. Only this one is a naught. So we still have this solution here left. Okay, so let's simplify this part. Okay, so we have this to be summation I from 1 to n xi yi. Okay, so I can multiply these two. I get this to be minus summation I from 1 to n yi summation I from 1 to n xi minus, or rather plus a1 summation I from 1 to n xi all square. All of this will be over n, so all of this over n minus ai or a1 summation I from 1 to n xi square equal to 0. So we've gone from this line to this line. This one here remains the same, all right, so minus a times b, so we're having summation yi summation xi. Note, it won't give you summation yi xi, please. It will be summation y summation x, like that. Then minus and minus is plus a1. Here I'll have summation xi summation x1, which is summation xi square, everything over n Then we have this one also. Please note that there's difference between summation x square and summation x square. They are different. They are different. So we cannot say that these two are the same. No, please, they are not the same. All right. So remember, our goal here was to get the value of a1. So I can see a1 here, and I can see a1 here. So I should factorize these two, and then take everything to the other side. So let's see what that becomes. Let's see what that becomes. Okay. So from here, picking only these two, I can see that if I factorize a1 from there, I'll be having 1 over n summation I from 1 to n xi all square for this part, all square. Then here, minus summation I from 1 to n xi square. Okay. So holding these two, don't forget we still have these two on this side. So we can take them to that side. It becomes equal to minus summation I from 1 to n xi plus 1 over n summation I from 1 to n xi summation I from 1 to n. Here I have this one to be plus, so it is changing to minus. Minus is changing to what? To plus. To plus. Again, the goal remains a1. So our a1 here can then become 1 over n summation I from 1 to n xi summation I from 1 to n yi, taking this one first, minus summation I from 1 to n xi yi over 1 over n summation I from 1 to n xi all square minus summation I from 1 to n xi square. So this is our a1. You can see that in this place there is no a naught. Everything we have here are values that we can get. Summation xi, summation yi, and so on. So all of these are quite easy to get. So this is our first solution. Of course, we can still simplify. We can multiply up and down by n so that we get our a1 to be equal to summation I from 1 to n xi summation I from 1 to n yi minus n summation I from 1 to n xi yi over summation xi square minus summation xi square. So this would form our a1. Okay, so it should be an n here. So this will form our a1. All right. Now remember or recall that we said that our a naught should be equal to summation I from 1 to n yi minus a1 summation I from 1 to n xi everything over n. So now that we know what a1 is, we can put it here and get what a naught should be in terms of xi, yi, and n. So let's quickly do that. So let's quickly do that. So we said our a naught should then be summation I from 1 to n yi minus, we know what a1 is already. A1 is all of this. So let's wait to put it there. So a1 is summation xi summation yi minus n summation xi yi. Don't forget our summation is going from 1 to n over summation xi square minus summation xi square. Everything times summation xi. Summation x. So let's see. Let's expand and see what this will become. So everything should be over n. So I have our a naught to be equal to 1 over n into summation yi. Now multiplying this one here should give us, so I have minus summation xi square, summation xi square, summation yi. Ow, I'm saying summation xi times summation xi. That's giving me summation xi square for this one only, then summation yi. Okay, and then the other one there would be, I'll be having that one to be a plus. In short, let me leave it as minus. Minus n summation xi summation xi yi over summation xi square in a bracket minus summation xi square. And we can close this part. Okay, so if this is clear, we can then get the LCM to see if it will make sense. So the LCM of these two, the LCM is what I have here. That's summation xi square minus summation xi square. So we are multiplying both of this. That is, we'll be having summation yi summation xi square for these two minus summation yi summation xi square for these two. Then here I'll be having these ones minus summation xi square summation yi plus n summation xi summation xi yi, like that. That is, I'm multiplying minus now by these two, so I have this will be minus then plus. Okay, so if that is clear, some things can go away. This one here and this one can go away, right? Because I'm saying summation y summation xi square, so these two can go away, but here they won't go away. So I have this to be 1 over n. Don't forget, this is our a naught. So our a naught is 1 over n into summation xi summation xi yi. For this one, that's an n somewhere here, n minus summation yi summation xi square over summation xi square minus summation xi square. So this is what we use to get our a naught. Already we know what we use to get our a1. So finally we can now go and say that yes, after we've gotten a naught and a1, our y can then be a naught plus a1x. We have fitted that set of data in what the polynomial of degree 1 . Okay, so if that makes sense, we'll go on to the one for a polynomial of degree 2. We'll go on to the one for a polynomial of degree 2. We'll go on to the one for the polynomial of degree 2. We'll go on to the one for polynomial of degree 2. Although these two formulas, this one here for a dot and for a1, it's I don't know. I should say it is not exactly necessary for us to come to this point. If you can easily go back here. So let me clean this part and then let me show us something. Don't forget, these are our a naught, this is our a1. This is what we'll be using. But I want to show us something else. Now remember we said that we want to minimize our residue. Now our S is giving us summation I from 1 to n yi minus a naught minus a1x all square minus a1xi all square. And then we said that our ds dA naught is minus 2 summation I from 1 to n yi minus a naught minus a1xi. We said it should be 0. It should be 0. Okay. Also, we said our ds dA1 is giving us minus 2 summation I from 1 to n xi yi minus a naught minus a1xi, and also it should be 0. It should be 0. Then from these two, from both of them, we agreed that the first part here can be summation yi, all right, minus na naught, okay, minus a1 summation xi equal to 0. Then we agree that this other one here can be summation xiyi, all right, minus a naught summation xi minus a1 summation xi square equal to 0. Remember, we know what these values are, all these y values, yi, xi, and the likes. So it means that from the given question, we can get summation xi, we can get summation yi, we can get summation xi square, and in fact, summation xiyi. So it means that this part here, this one, this one, this one, this one, and this one will all become numbers. So it means that we will be left with simultaneous equation of two variables. So where a dot and a1 are our variables. So it means that if you can solve from here directly, we would not need to go on to get all the distance. As I said, that this part here is not exactly necessary. So if you can get it from here directly, no problem. No problem. Example. So I'll be solving using this part. Example. Example. Use the least square method to fit the line a plus bx for 2, 1 over 6, 5 over 6 minus 3 over 2, minus 2 and minus 1 over 3, minus 2 over 3. So here we've been given our xi and yi values. So this is x naught, y naught, x1, y1, and so on. Okay. So for me, I like putting all of this in a table so that we will see clearly what we want to do. I like putting it in the table. So let's see what our table looks like. The table, so xi and then yi. Our x values, we have 2, we have 1 over 6, we have minus 3 over 2, and then we have minus 1 over 3. The y values, we have 1, 5 over 6, minus 2, and minus 2 over 3. Now, from what we agreed on here, it says we should go and get summation yi. We should get summation. So it means that we should go and add all these y values, all these x values. It goes on and says that we should go and multiply x and y and get the summation. Then we should get xi square also. So let's go. We need xi square. Okay. So we want to square all these values now. 2 square is 4. 1 over 6 square is 1 over 36. This one here will give me 9 over 4. And this one here is 1 over 9. Okay. So again, it says we need xiyi. So I can come here and get a particular xiyi by multiplying these two things. So 2 times 1, 2. This 2, that's 5 over 36. This 2, that's 3. Then this 2 will give me 2 over 9. So our formula requires us to add all these things together. So let's go and get summation xi. So from here, our summation xi will be, so 2, adding all of this together, we'll get so 2 plus 1 over 6 minus 3 over 2 minus 1 over 3. We get 1 over 3 for summation x. So this is 1 over 3 for summation xi. Don't forget 1 over 3. So whatever you get here is for summation yi. Okay, that one will be 1 plus 5 over 6 minus 2 minus 2 over 3. So this is minus 5 over 6 for summation yi. Next thing is for summation xi square. So we have 4 plus 1 over 36 plus 9 over 4 plus 1 over 9. So this is 115 over 16. The next one is summation xiyi, which is 2 plus 5 over 36 plus 3 plus 2 over 9, which gives 193 over 36. Remember, these are our formulas. This is all we are using. So please, if I don't use it, I can go and take that our a naught and a1 values. No problem also. Or maybe I should even do that. Our a naught is given as what? It is given as so 1 over n, Abi. Okay. Summation yi minus 8. No, this is not what I want. This is not what I want. My a naught is 1 over n summation xi yi minus summation yi summation xi square over summation xi square minus summation xi square, like this. So this is what we got when we did that a naught. Okay, so we know what all of these are. Of course, our n is the number of I values here. So we have 1, 2, 3, 4. 1, 2, 3, 4. So our n is 4. So we get our a naught to be equal to 1 over 4. Actually, there's an n somewhere here. There should be an n somewhere here. So this should be n here, n here. Okay, there should be n here, and there should be n somewhere else also. I think here. Let me confirm. Let me check. This one. So there should be n here. Abi? Okay. Okay, so we have our a naught here to be 1 over 4 times 4. I have 4 here. The solution xi is already 1 over 3. Solution xiyi is already 193 over 36. Okay. Minus summation yi is minus 5 over 6 times xi square is 115 over 16 over our n again is 4. Summation xi square is 115 over 16 minus summation xi square, which is okay, we didn't get xi square. Oh, sorry. Summation xi all square here is supposed to be 1 over 3 square. So this is supposed to be 1 over 3 all square. Same thing here. 1 over 3 all square. It is summation xi. Then we are squaring it. Then we have this one to be minus summation xi squared now, which is minus 115 over 16. Okay, so we are good. So it remains for us to go and use our calculator. So we can have our a naught to be equal to, using your calculator, we'll get 1 over 4 times 4 over 3, 4 over 3 times 193 over 36 plus 5 over 6 times 1 over 9 over 4 times 1 over 9 minus 115 over 16 minus 115 over 16. So let's see what that gives us. So we get this to be minus 782 over 2913. So this is our a naught. So we'll go on to get what a1 is. We'll go and get what a1 is. Of course, we know the formula for a1 also. All right, but left to me, I won't go with this because I cannot cram this formula. So rather, I will know that this is my residue, differentiate it to get these two results, then put in all the values there so that we can solve for a naught and a1. Because you agree with that, we are still going to do the same thing again for a polynomial of degree 2. So it means that we no need to know the formula for a naught, a1, and a2 in that one also. So it makes no sense. If you can just easily know this formula, then you can solve for a naught and a1 here. Okay, so let's finish this one. Let's finish. This is our a naught. It remains a1. So what's the formula for a1? I can't remember. So a1 is summation xi summation yi minus summation n summation xi yi over summation xi all squared minus n summation xi squared. So we have this to be, our summation xi is 1 over 3 times summation yi is minus 5 over 6 minus n remains 4. Summation xi yi is 193 over 36. So over we have summation xi all square, which should be 1 over 3 all square minus 4 times summation xi square is 115 over 16. So using our calculator, we get this to be so 1 over 3, or better still, minus 5 over 18 minus 193 over 9. Everything over 1 over 9 minus 115 over 4. So our answer here is 782 over 1031. Remember, we said we want to fit it to a polynomial of the form a plus bx. So our y is equal to a plus bx, or better still, a naught plus a1x. So add on my alphabet in this place. So my a here is a naught, my b is a1. So we have our result to be a naught is minus 782 over 2913 plus a1 782 over 1031x. So by doing this, we've fitted this sets of points to this given polynomial, or to this polynomial, and that's a polynomial of degree 1. That's a polynomial of degree 1. Now please note that this is co-fitting. We are not required to get exactly the same result. What do I mean? Not ideally, if we put, like, for example, we have our y to be equal to f of x, right? If you put x value, we should be getting our y back. So normally, if we put 2, we should be getting 1. We should be getting 5 for this one or this one. But since we are fitting the curve, we are not saying that this is the function that is producing these things exactly. No, it is like saying that I have it's like saying I have things like this. So I have my graph. Okay, this is my x1 y I naught, x2 y2, and so on. Now I want to fit a polynomial of degree 1. It's something like this, like line of best fit, something like this. You can say that when I have my x naught, I will not have directly y naught. I'll be having something close to it. You get? So here, if we put 2, we should not expect to get 1 directly. We'll be getting something close to 1. So the higher our polynomial is, the more accurate our result will be. So it means that a polynomial of degree 2 will be more accurate than a polynomial of degree 1, and so on. So let's see what this polynomial here gives us if we put in 2. We put in 2. So I have minus 782 over 2913 plus 2 times 782 divided by 1031. So the answer is 1.24. It is not 1. It is, so here now, our y of 2 is 1.24, not 1. So it means that we are in a way accurate. No, sorry, we are in a way correct, not exactly accurate. Okay, if you put this one also, you get something close to 5/6, not 5/6. Say I have this to be, let me put it now. If I put 2, I have so this is 1/6. No, okay. Over 6. So I'm getting this to be, sorry, I'm not getting this. 1/6 times 782 divided by 1031. I'm getting this to be minus 0.14. Minus 0.14. Now note that 5/6 is 0.83. So again, we are not saying that it will be accurate, but it will be a result close to that number. So it is like what we do in our physics, drawing our line of the S fit. So it will exactly be this result, something close. So this is for a polynomial of degree 1. Let's go on to polynomial of degree 2 and see what we have. Okay. So for a polynomial of degree 2, we are following the same approach, except that for that one, I will not be solving for a0, a1, a2 because I've already said that it is a waste of time for me to. So remember, now we are saying we want to get our y to be equal to a0 plus a1x plus a2x squared. This is for polynomial of degree 2. Again, our residue, we said our residue is yi minus yi summation all square. So our residue should be summation I from 1 to n yi minus a0 minus a1 xi minus a2 xi square all square. So again here we want to go and get want to minimize this. You want to minimize it, so I have the s, the ai to be 0. So starting with a0, again we have our the s, the a0 to be equal to minus 2 summation I from 1 to n, all right, yi minus a0 minus a1 xi minus a2 xi square. Here we're differentiating a naught, so every one will be 0. Yeah, you're having minus 1 left here, minus 1. Okay, of course it should be 0. It should be 0. The a1 here will be minus 2 again, summation I from 1 to n. So here we're having xi times everything we have here. That's yi minus a naught minus a1 xi minus a2 xi square, and it should also be 0. So same even thing for the a2, the a2. So here again we'll be having minus 2, in fact minus 4, but let's have minus 2. Minus 2 summation I from 1 to n. Want to differentiate a2 here, a2, so we'll be left with xi square. Fine, so I have this to be xi square times yi minus a naught minus a1 xi minus a2 xi square, and it will be equal to 0. So let's see, we want to take away all these minus 2's and then expand the summations for everything. So let's see what we have. Of course, don't forget your summation a naught will always be n a naught at this point here. So I have this first part here to be, so I want to write our statement here. So it is implying that, so all these three implies that, so here I'll be having summation yi, please pardon me, I want to ignore this counter. I want to end the summation yi. This one here I'll be having minus n a naught minus n a naught. Why? Because I'm having it to be summation a naught from 1 to n. That's n a naught. The next one will be minus a1 summation xi, right? Then minus a2 summation xi square equal to 0 for this first one. Coming to the second one, I'll be having this to be summation xiyi for these two. All right, now this two, it will be minus a naught summation xi, right? For these two here, it will be minus a1 summation xi square. Please don't be lost. I'm multiplying xi and xi. That's xi square. A1 is coming out of the summation sign. And the last one will be minus a2 summation xi cube. Everything equal to 0. Coming to the last one, we have this to be summation xi square yi. All right. The next one will be minus a naught summation xi square, all right, minus a1 summation xi cube minus a2 summation xi to power 4. Everything is equal to 0. So it means that if you can remember all of this, of course we know how to get summation yi and xi. We can easily solve for what? Solve for a naught, a1, a2, so that our polynomial will be of the form y equal to a naught plus a1x plus a2x squared. So this is the least square approximation for fitting a set of data on a curve of polynomial of degree 1 or degree 2 or degree 2 or degree 2. So if this makes sense, I'll be taking an example for this one, because I do not want to waste our time. So instead, what I'll do is I'll give us an alternate approach to solving this problem, or to doing things like this. So if we don't want to go and be minimizing residue, blah blah, and we want a better way, then we can easily do it. Okay, so let's take the alternative. So please note this is one. This is for polynomial of degree 2. We did for polynomial of degree 1 earlier. Fine. Even for the degree 1, you can choose not to use those A dot and A1 formula. Just come and use something like this that we did for that one, and then you're good. So the alternative formula or the alternative method of solving this, still on discrete least square, still on, so alternatively, we are still on least square approximation, please. Least square approximation. So basically, the goal of minimizing this residue is to get to these equations, right? Is to come here. That's the goal of everything we've been doing. We want to do this. Even if it's for a polynomial of degree 3, we want to get 4 equations that we can get what our A0, A1, A2, A3, right? So let's see how we can easily get this formula without necessarily going through all of this. So the formula is quite simple. We will be using the matrix approach. Remember when we did our linear algebra, we said that for a system of linear equation, we can write it in the form y equal to ax, something like this. Am I correct? Sorry. It is ax equal to b. Yes, where a is the matrix of all coefficients, which are the variables, and b are the constants. Something like this. We are starting with this a. So our a in this case is starting with n summation x square summation x cube, right? And so on. See what I'm following? Summation x to power 0 to power 3 and so on, right? Same thing is also summation x, right? Summation x square and so on. You get? So what should we have here to fill it up? Summation x square, summation x cube, and so on. Abi? Here, summation x cube, summation x4, and so on. Here, and so on, right? This is our a. Now x, what are x? X are what are unknowns. What are the unknowns here? The a values. You get? So here I'll be writing this to be a0, a1, a2, a3, and so on. Now our b are the ones with y. So here I'll be writing this to be summation yi. Now someone will be thinking about summation yi square. No. So be summation xi summation xi square yi. So yi is the same. So it's like saying I'm having x to power n yi. So you get, so x1, x2, what will be the next one? Summation x cube I, yi, and so on. So if we need to get a polynomial of degree 1, what does that mean? We are dealing with just two what? Unknowns, Abi? So we come and take a polynomial we come and take a 2 by matrix 2 by 2 for this guy, 2 by 2, 2 unknowns, then 2 of this guy. Is that okay? Polynomial of degree 2, 3 unknowns, Abi? So we have 3 by 3 and 3 of this. You get? So this is what I'm trying to say here. I want us to come and get this formula here. We want to get this back. Don't forget, n is the number of terms we have, Abi now. So for degree 2, please keep this formula somewhere so that we don't miss it. So that we will compare it later on. Well, for now, I want to clean. So for degree 2, we said that we are dealing with 3 unknowns. So I'll be taking 3 by 3 matrix. So I have this to be n summation x square. Please, all these x are supposed to be xi. Summation xi square. Summation xi square. Summation xi cube. Summation xi square. Summation xi cube. Summation xi to power 4. All of this times a0 times a1, a2, and it is equal to summation yi summation xi summation xi square yi. Don't forget, how do you multiply matches? How do you multiply? We multiply row by everything we have now. So I have this to be na naught abi now plus a1 summation xi plus a2 summation xi square, right? What should it be equal to? Summation yi. How about the next line? The next line is a naught summation xi plus a1 summation